OK, so let's talk about some of the other things that were on our list of limiters to instruction level parallelism, and ask ourselves, are these things which we can solve very easily? Well, things start to get harder pretty fast here. Like I said, dynamic events, they're basically things the compiler has no way of reacting to. Now, the instruction set might be able to react to it. You can add things into the instruction set. You can maybe take a branch dependent on a dynamic event. But let's look at some dynamic events. First dynamic event here, cache miss. Well, it's really hard for a compiler, just all things being equal, knowing whether a load is going to take a cache miss or not. It might have some guesses, and that could influence the code. But actually doing something about it. If you think about what an out-of-order superscalar does, if you take a cache miss, it'll reschedule the code around the cache miss. It'll take the non-dependent instructions, the instructions that are not dependent on the load, and pull those up and try to execute those. But if the load hits in the cache, you want a totally different schedule. You want to actually try to start executing the instructions that are dependent on that load as soon as possible. So an out-of-order superscalar has dynamic means to be able to do this. It has dynamic instruction execution. But our VLIW processor, which is statically scheduled, can't really do this. So what's some techniques to go about after this? One thing is something called informing loads. As far as I know, this actually has not been built in any hardware, but it's been proposed, at least in the computer architecture academic circles or in the computer architecture literature. And informing loads was actually come up, the original paper about this is by one of our faculty members, here at Princeton. Margaret Maranozzi wrote she's one of the authors of this paper. But the basic idea is that if you have a load that misses in the cache, you can not execute subsequent instructions. Else, you can or there's actually no else there. If the load misses in the cache, you just don't execute some subsequent instructions. You can basically nullify those instructions. And this allows you to change the code sequence dependent on whether the load hits in the cache or whether it misses in the cache. And this was done with Todd Mowry, Professor Margaret Maranozzi, and Professor Todd Mowry, I think both when they were graduate students. And Mark Horowitz from Stanford was on this paper. I think a couple. I don't remember who's the last author, the professor on this work. Another option is something that the Elbrus processor people did. So you've probably never heard of this processor. It was something that was built in the, well, I actually don't know if it was ever finished. I think they had a prototype of it. Sort of in the Soviet Russia day, right when the Soviet Union was kind of breaking down. This was the design house in Soviet Russia, which made all of these sort of military processors. They later went off, and that same design team was going to go build some commercial processors after the fall of the Soviet Union. So they went and they went to go build this processor, and it's a VLIW processor. It's some very long instruction word processor, and they had an instruction in there which tried to solve this dynamic event problem around cache misses. So what it said is, if an instruction misses in the cache, go execute a different piece of code with a different schedule than if the instruction, if a load hit in the cache. So you could effectively have two different code sequences. The compiler could actually generate two different code sequences, and you can get back a lot of the performance and get back to almost exactly what an out-of-order superscalar could do. Now, this processor never really made it commercially, and later the company went under and was bought. I actually don't know if the assets were bought by Intel, but at least all the people who worked at this company now work at Intel effectively. So they still live in Russia. So that's a funny story there that, yeah, it didn't work out from a commercial perspective, but they had some cool ideas in there that you could actually try to schedule around schedule around cache misses. OK, so some other things. Branch mispredicts. Well, we already talked about one technique here, when you talk about you can add predication. But that doesn't help if you have big pieces of code, big code sequences, and big code hammocks. You can't necessarily predicate your entire program. So what do you do instead? Well, one solution that people have come up with for this, and this is a hard one to deal with here, is you can add branch delay slots. So you have a VLIW processor, let's say it's 3 wide, and you add branch delay slots in your instruction set, and then you use predication in the branch delay slots. And what this allows you to do is it effectively lets you mask some of the branch mispredict penalty and change the code schedule a little bit dependent on the prediction. Or change it actually completely based on what the branch is. And the way this works is in the delay slots, you use the same predicate that the branch is branching on. So the branch is branching on, let's say, if A equals B. Well, you use that same thing in the predication, and effectively you can reschedule the code differently depending on whether the branch is taken or not taken. And because you're putting it in the delay slot, you can sort of get around some of the problems here of whether it's taking the one direction or taking the other direction, no matter which way the mispredict happens, or whether the branches can be predicted correctly or not. And what we're doing is basically putting code in the delay slots that will always execute, but it can be predicated, and you can effectively pull code up from the 2 destinations of the 2 branches. So it's sort of a way to get around branch mispredict penalties here. This is actually done in a research processor that was built at MIT. And I think this is probably also done in some of the other HP processors. But the MIT processor, at least, was called the M machine out of Bill Daly's group. He's now at Stanford, but I think the M machine was sort of built right when he was moving from MIT to Stanford. But they had, I think, 3 delay slots, and they were 3 wide, and they could predicate the instructions in the delay slots. So last thing is exceptions. So you take an exception, and you want to schedule different code. And these are like impossible to predict. The compiler has no way to try to predict this. But this is hard on a superscalar also. When you have a traditional superscalar and an exception happens, they usually end up flushing the pipe anyway. So, and it doesn't happen that often. It probably doesn't hurt your performance that much. So no one's going to lose too much sleep over this one. So I briefly wanted to say something about how to build really wide VLIWs. As we start to go to wider and wider VLIWs, lots of instructions execute at the same time, you have to start thinking about what does the register file in the bypass network look like. So in this drawing here, we actually have a figure of the C64000 series processors. So these are TI DSPs, sort of the flagship DSP processors. And this is a sort of block level diagram of what they have. And what they actually have is they've divided the machine into local register files when they bypass inside of what's called a cluster. So it's a clustered VLIW. It's similar to how we have clustered superscalars, which also divide the register file. But this is an architectural, a big A architectural or ISA level architecture splitting or dividing going on here. So in something like the C64000, they actually have 4 instructions per cluster, so they're executing 8 instructions at the same time. And you can bypass values between these 4 ALUs within them, or you can bypass within these. But if you want to sort of take a value from here and move it to there, you have a very low bandwidth sort of bypass path here, and it takes an instruction. You effectively have to have a move instruction to move between the 2 different clusters. So there's a lower bandwidth between the clusters and a higher latency between the clusters, but inside of a cluster it's very fast. And what's important to know here is these are not 2 processors. These are all executing 1 instruction at the same time. So it's an 8 wide instruction executing on these 8 different ALUs. And this is used in as I said, the TI high-end DSPs. Also, it's used in HP's and ST Micro's LX processor. This is probably a processor you never heard about, but this was actually what Josh Fisher went on to go do at HP Labs after multiflow. So this is after sort of a lot of the original VLIW work. Same person. Went and built this LX processor, and this is sort of a joint collaboration between ST Micro and HP, and this shows up in printers today. So it's not something you're going to really have. The LX processor is probably something you're not going to have in your desktop machine.